So today we're going to do a slight detour. We're going to get back to navigation by individuals, but we're going to do a slight detour on biofilms. There are these objects. Before I go into this, I just wanted to start from what from my argument from yesterday, because it created some confusion. So if you give me like 10 minutes, is that useful? I spent 10 minutes to explain that last part that was going on over there. Okay. So the idea from last lecture, I remind you, is that so we have this chemotactic response. We have found out that if the system is linear, that chemotactic response produces a behavior that is response to a gradient measured in time. And then we decided to verify whether that was a good idea or not to measure gradients in time. And we happened to calculate how many molecules of a chemoattractant, so of a chemical dispersed in the environment, would bump into a perfect absorber. Okay? And we calculated it by saying, okay, we're at low Peclet numbers. Okay, remember, this is an important number. So this chemical that we think about as a field, as a continuum field, will diffuse. And so we just calculated the flux, the diffusive flux that arrives to a spherical absorber. So imposing that the concentration here is 0 and the concentration here is a given finite number. And it turned out that this flux was proportional to the radius of the spherical absorber. And I told you that this was a profound result, and it just went over there and tried to show this to you, and this was too quick, so it created some confusion. So I'm just going to repeat the argument. And the idea is that this is a continuum way of thinking about how many molecules the bacterium will sense, but there is an equivalent way of thinking about it, which is discrete. Okay? This was continuous. Okay? So you imagine that instead of having a field of concentration, you think about each molecule and you model it as a random walker. The molecules will, there is no advection, so they'll just go left and right in, with equal probabilities. And then I argued that the Fokker-Planck equation for the probability that a random walker is at a certain position in space followed a diffusion equation. Okay? And the argument went through just thinking about in a one-dimensional, in one dimension, you have random walkers at each of a set of discrete locations. These discrete locations are separated by a step delta, and you think about how many walkers will jump left and right at the next time step. Okay, so you discretize space and time, and by this argument, I won't repeat it because it's 2 lines, but by this argument, you can demonstrate that P, where now P is the probability that a random walker, so P is a function of x and t. It was discrete in the derivation, but you can take the limit for delta that goes to 0. And now P follows the diffusion equation. Okay? And so, okay, so this was the first part. And then I mentioned, without proving anything, that the fact that this R, that this flux is proportional to R, can be understood by the fact that random walkers in the vicinity of a surface will hang out for a long time before wandering away to infinity. Okay? Is it cool until here? Okay. So this is just 2 ways of looking at the same thing. Okay. So how do we go about to demonstrate what I just told you? So, okay. So to do this, what you have to do is, so we have this, and I just want to say that this goes with the following result, which is that P of capture is proportional to R. In fact, it's R divided by, let's say, B, the starting location. I'll sketch what I'm talking about. And this goes with the following result. Sorry. Okay, so what I'm about to demonstrate, and it's going to be quick but hopefully clear, is that the probability to capture a random walker, so imagine you have this spherical absorber and your random walkers start from a certain location at distance B from the center, and this is R and this is B. Okay, so we think about this spherical shell. This probability goes like R, the radius of the absorber, divided by D. Okay, and this goes with, if this is true, then I can demonstrate, and that's pretty quick, that the number of times a random walker starting from here will bump into the absorber goes like B, so its initial distance from the center, divided by B minus R. So the distance of the walker at time 0 from the absorber. Okay, so you can see that if you are close to an absorber, you'll hang out there for a long time. You'll bump into it for n that can become infinite. Okay, it doesn't go to infinity for real because this breaks down at small enough scales, but it's pretty large. Okay, and this is has very profound consequences for chemotaxis because, of course, if you are now a bacterium and you have to cover your surface in receptors that will bind that ligand and measure and count how many molecules are in the environment to decide whether you should keep running or tumble, then you really want to know what's the probability that the ligand will bump into a receptor. And because the ligand keeps bumping onto the surface, even if the surface is not completely covered in receptors, you can have a pretty high efficiency. Okay, so this shapes the way that bacteria cover their surface in receptors. There's a lot of work, really nice work, on this stuff that I'm not gonna talk about. Okay, so let's believe this for 1 second and let's calculate this. Okay, so if this is the probability to be captured, the probability to wander to infinity is 1 minus the probability to capture. Okay, and so how do I calculate n? I simply say that this is the sum of n times what's the probability to bump into the absorber n times. Well, I need to do the back and forth n times, so I have P of capture to the power n times, then I have to wander to infinity. Okay? And so if you expand that, you take 1 PC and 1 minus PC outside of the sum, and this remains like this. Okay? For n equals 0, this is 0, so it doesn't matter. N equal 1, you have 1 times P to the 0, so this series is 1 plus 2 times P plus 3 P squared, Okay, and this is the Taylor expansion of, so the sum converges to 1 over 1 minus PC squared. If you do the Taylor expansion of 1 divided 1 minus PC squared, you'll get exactly that series. Okay? Okay, so we are done here. We have PC. We have 1 minus PC at the numerator, 1 minus PC squared at the denominator. So it is like this. Okay, and if you now believe me that this is right, we have the result, which is what I told you before. Okay, so it's not an explanation right now. If you believe that P of capture is like this, then the number of times you bump into the absorber is pretty large. You can do the reverse. I don't remember how you do it, and I think it might be complicated, but it doesn't matter. The intuition behind this is this result goes with the fact that the random walker hangs out for a long time around surfaces. And I think I've stressed the message enough. So unless you have questions, I'd pass to the next topic. Yes?
You said there you said the average of n is p over p minus r, but there is r over.
Oh, sorry. I think this is the right one, because the calculation says that it's this, right? PC is r over b. This is definitely right because it's smaller than 1, so it must, I bet this is the right one. Let's see my notes. Yes. Thank you.
The result depends on the dimension because of the capture.
Yes. Absolutely. This, by the way, P capture, the probability for a random walker to be captured, because it solves the Laplace equation, it's also called the harmonic measure. So there's a lot of math, really interesting, deep math, that computes harmonic measures for boundaries, very complicated in different dimensions. And this is particularly interesting in 2 dimensions, because in 2 dimensions some harmonic functions are conformal invariant, and this is a huge group, and so there's a stream of really beautiful math, and which I'm not going to talk about. Yes?
R over B is independent of dimension, like the problem.
No, it depends on the dimension, definitely. This is in 3D. This is in 3D because this is spherical. I don't know how it looks like in 2D, but you can calculate it for a circle, that's for sure.
Would we have the same structure of the diverging number of bumpings also in dimension 2? Or
With this,
the fact that the average of n diverges when B approaches 5?
so I think it changes because in different dimensions, it might be even stronger in smaller dimensions, because like random walkers have a probability 1 to get back to the original location in 1 dimension.
Okay.
So it will probably vary, but yeah.
Can you say again how much was P infinity?
P infinity.
1 minus P.
Sorry, this is the probability to wander away to infinity.
Okay.
So it's 1 minus the probability to be captured.
Basically.
Yeah. So that means that you are going away before bumping into the absorber. Okay. Yes.
And that capital B is just a number depending on the dimension.
Capital B. Where is capital B?
The average n.
It's a little bit.
This is a small. This is a small b. Okay. Let me write this down again. This is right. So the calculation is right. Do the math. That's the bottom line. Don't try to remember it. At least for me, this is definitely true. Sorry, b minus 1. Okay, it's this one. Why do I have to write it again? Okay. Cool? Okay. Okay, good. So, small detour. These are still bacteria. It's clearly a very different scale that we're talking about. I think these are interesting objects for various reasons. So I'll give you my very short introduction about why I think biofilms are cool. Already this is a nice movie, so that's already a reason why one should work on this problem. Okay, we've talked about these individual cells, okay, for a bunch yesterday. And then a biofilm is what happens to individual cells when they arrive to surfaces. Interfaces, actually, they can be pretty broad. And we're going to talk about interfaces between a solid and air, so particularly an agar gel and air, but this is a very loose definition of interfaces, and you have biofilms occurring at any kind of interface. Okay, so the first thing that happens when a single cell arrives at a surface is crowding. You have a lot of other cells, and they are kind of stuck because they're not really able to move if the agar gel is solid enough. I'm going to talk about Bacillus subtilis, but this is the phenomenology is kind of conserved. Okay, so if you have this crowding phenomenon, then a lot of times what happens is that there is differentiation. So most cells will lose their flagella, or actually they declutch it from the motor, so they cannot use it. It's not like they destroy it, but they just cannot use it anymore. So they suddenly they become passive. So we've talked about, all of the problems, the troubles they go through to behave reasonably and to chemotax to reasonable places. And then the moment they arrive to surfaces, they just drop all of that. And then in exchange, they start to produce stuff that goes in the extracellular space. And I'm saying stuff to stress the fact that there is a variety of things that they do. Every different bug is different. But this stuff is mainly made of polymers, and it turns this collection of cells into a material. So you can think about this collectives as materials, really. And what's interesting to me is a lot of people study biofilms because when they do these transitions, the cells sort of become really resistant, and it's hard to kill them and to remove them, and they cause a lot of problems. Sometimes they are used, actually more and more, they're used for biofiltration and other technologies, so they can also be put to work. But to me, what's interesting about biofilms is that there is a lot of information now about these kind of patterns. So it doesn't matter what the colors are. These are different genes. They're expressed in different locations in the biofilm, and these patterns are pretty well conserved. They're pretty broad. You measure them in different biofilms in different conditions. And this kind of resembles what happens for example, in embryogenesis, but it has nothing to do with it, right? There's not an adult biofilm and a baby biofilm. There's not an embryo. There's no arms. There's no wings. There's nothing that the biofilm does that we are aware of that would need gene expression patterns. Now, I'm being a little extreme to convey the point. There are things that we know about, but it's a very young field where we don't have a real intuition about the connection between these gene expression patterns and potential biofilm physiologies, so multicellular physiologies. So this is what got me into this field, and I'll mention two examples about functions that might be associated to gene expression. This is what we'll talk about later today, so in this lecture, so I'm not going to talk about it. This is, again, a biofilm, and you've seen it in the first movie. It's full of wrinkles. These wrinkles are caused by the fact that there are these polymers, so the biofilm is a material, and so it can wrinkle, as a material does. Elastic instabilities create these wrinkles, okay? And one very interesting thing that's also connected to Eleni's work, very much so, is that when the biofilm becomes large enough, these wrinkles form, so gene expression, wrinkle formation, and then circulatory system. Because below these wrinkles, there are channels. And these channels allow nutrient to flow through the biofilm. And this really reminds us about what Eleni told us yesterday. It's becoming large enough that diffusion is not enough. That nutrient coming from the sides, from below, is just not enough. So you need stuff to get in by advection rather than diffusion, and this requires a circulatory system. The interesting thing is that you don't only need the system, you need a pump. And in this system, it looks like evaporation, differential evaporation drives the flow. So really, I really love this work. And it's one way to connect matrix production to a function. Okay, and then I'll mention another one, which is the following. Here also you see a biofilm, although it's slightly more subtle. It's this band, this dark gray band. This is liquid, this is air, this is a martini glass, and this is also called a biofilm because this is an interface, and if you throw bacteria in this liquid medium and you wait long enough, they'll chemotax to the surface to find oxygen, and then they'll remain there, they're stuck, and they make biofilms. And one interesting thing is that in Bacillus subtilis, one of the stuff that the cells produce is surfactin, which is a molecule that's a surfactant. So it modifies surface tension, and in this case, it is used by the biofilm to climb the wall of the martini glass. So you see, this is dark gray. That's where the biofilm is, but this light gray is where it has climbed. Okay. So this, yes.
So for the definition of a biofilm, is there kind of a criteria that it's somehow percolated network, or
it's not very precisely because I think we are willing to call biofilms pretty much anything. The two things, no, exactly. So the two things that need to happen are matrix production, so that makes the things stick, and a kind of interface. These are the two things that need to happen. People will argue that different things, but I think this is the consensus right now. Okay, and we're going to talk about that phenomenon, which started from the following observation. So these are three biofilms of Bacillus subtilis that are growing in time on a Petri dish. These are different times, 6, 12, 24, and 30. And the first thing we observe is that they spread. You've seen it in the first movie as well. Okay. Interestingly, it doesn't matter whether you have flagella or not. Hardly at all. This is just one colony. This is the physicist who makes experiments, and so I did, I think, 30 colonies, and I did the standard deviation, so it's reproducible, it's blah, blah, blah. Okay, it doesn't matter. The flagellum doesn't matter. And then suddenly you knock out the EPS. The EPS is an exopolysaccharide, so it's a complex sugar. It's one of the main components of the matrix that we just talked about for Bacillus subtilis, and it has an entire operon in the genome of the cell that is required to assemble this sugar. Okay, so you take the entire operon off, so these cells are not able to produce that polymer, and suddenly, although producing the polymer is costly, the biofilm doesn't spread as much. And again, 30 biofilms later, I can confirm that this is statistically significant and it's reproducible. Okay, great. So this is kind of puzzling for two reasons. The first reason is that producing polymers is costly, as I just said. And the second reason is that from a physical point of view, I just told you that The matrix is what makes this material cohere, so it's what causes it to be rigid, to be very viscous. So to me, it sounded like when I saw this first, I was like, well, this is unintuitive, because I would assume that these guys having a lot of this matrix would be much more viscous, much more tough to expand. How is it that they expand faster? Or is it obvious to you? This is unintuitive, right? At first sight. You would agree? No answer. Okay. So the idea here is what I sketched before, and it's the following. So the polymers, sure, they're costly. Sure, they make the biofilm more sticky and more viscous, but they do something else that's interesting. I'll leave this up for a little while more, and then I'll erase that later. They do something else, which is they modify the free energy in the system, right? So let's assume for a second that this is a material. It's in a closed environment, and let's think about it as in contact with the substrate. Okay, here's the substrate. And here, let's assume the cells are dead. Okay, nothing happens. There are cells, there are polymers. Okay, the system is in equilibrium. But cells are not dead, and what they do is they consume water and nutrient to produce more polymers and more cells. So in particular, this will modify the volume fraction of the polymers. Phi is the volume fraction of the polymers. Okay, so this will drive the system out of equilibrium. Luckily, just slightly out of equilibrium, because everything is very slow. Okay, but so what the system will try to do will be to try and equilibrate this fluctuation in polymer concentration that occurred because the cells are not dead. Okay, and so what do you think will happen? The substrate is a hydrogel. So it's an agar gel. There are these cross-linked polymers, and it's full of water. Okay, so what do you think will happen in the system? How would you make this fluctuation in polymer concentration vanish? It cannot, but that would be a great idea. What else can happen? If the polymer cannot cross to go to the agar gel, what else can happen? Can something else move across the surface, you think? The water. In which direction? Up or down? Up. Okay. Great. So from this very down-to-earth point of view, we infer that just producing these polymers will make the biofilm change its volume, right? Because it will make water flow from the agar substrate to the biofilm, and this will make the biofilm changes its shape. Do you think it will be more like this or more like this? Who votes for this? Who votes for this? Everybody thinks it expands. Okay, great. Let's assume there is, okay, now you have to tell me how, right? Everybody thinks it expands. Great. Okay, so here is the biofilm, and it's, according to you, it's expanding, and here is the substrate, okay, and this is solid, and this is also solid, So if you think about this, for example, as a Newtonian fluid, it will be more complicated, but let's assume it's a composition of water and biomass. So a two fluid mixture of two Newtonian fluids of potentially different viscosities. What happens here when you have the substrate that is still and the biofilm that's moving? What happens at the interface? If I have a velocity gradient here, if I have a velocity here for the biofilm, how should the velocity be at the interface between the biofilm and the agar? It should be? It's no slip. Why is it no slip? Because there's friction, right? I mean, the thing that we are trying to model is something that is still connected to a fluid that's trying to move. And if you're trying to move a fluid, you have to cope with no slip conditions. As soon as there is an interface, the fluid will not want to move at interfaces. And this can change slightly if you go very weird things, but basically you can't get around it. Okay, so now you have, because everybody thought that it would expand, now you tell me what's the force that makes it expand. Ideas? Yes? Sorry? Gravity. Gravity in what direction? Oh, like if you have a drop that is not in equilibrium, and then there is gravity, and then it does this. But then it stops. The moment it arrives to equilibrium, it stops. Okay. Any other idea for continued motion? Yes? The colony keeps growing. Yes?
So, gradient of concentration.
These are two different ideas, I think, and they're both right. Okay? So we have to do some math to demonstrate it, but these two ideas, if I rephrase them, is one, the biofilm is producing biomass. Okay, so there is way for the biofilm to exert forces just by increasing the biomass, which is, you proposed it, so what would that be? How would you generate forces by producing biomass? Pressure? Pressure between what? Exactly. So bacteria push what? The other bacteria. So this requires that bacteria are in contact. Okay, and this is right here. If you zoom into this region of the biofilm, you have monolayers of bacteria that would perfectly fit Lisa's talk from today. They are modeled as liquid nematics. They are pretty cool. You look at them, the orientation matter, they touch. So the moment you create a new cell, that will push the next one. Okay, but this is not what happens in the bulk. Okay, so we'll talk about this. I'll show you data for this, but for the moment, believe me, this cannot account for any spreading of the bulk of the biofilm because they are not touching each other. They don't touch each other. They're not at such a high density that it can just push against the next one. So what can make the biofilm move is, as proposed by this guy here, gradients. Okay, gradients in densities of the polymers that create differences in the chemical potential of water that will want to go one way or another. Okay, and these gradients, we are not done. This is just an idea. These gradients will make the biofilm expand horizontally because they end up being mostly in the horizontal direction. Okay, we have to do some math to demonstrate that this is true. Any other ideas?
How about the surface condition?
surface tension is a great one. So if you do, so because I showed you in the pellicle case, that was able to make them move up. If you make a calculation and you calculate what is the extent of surface tension, how much force you could exert on a biofilm, because at the solid air interface, biofilms are much tougher, that wouldn't be enough. But that would be a very good idea. Yes, very good idea. And the last one, which is connected somehow to surface tension, is wetting, and I'll discuss that later. But for the moment, let's ignore it. Okay, so how do I go about taking this down first? No, it's this that goes up. Okay. Uh-oh. Okay. I'll move to the other one. Okay. Okay, how do I go about this? I will as I said, I will think about this biofilm as a mixture of two Newtonian fluids. Okay, so phi will be the volume fraction of the biomass, and 1 minus phi will be the volume fraction of water. Okay, so in each, I'm trying to construct a continuum model. So I'll take a little volume, and in this volume there will be some biomass, and the rest will be water. Okay? What else should I tell you? For the moment, nothing else. Okay, and I said that this is a system that's slightly out of equilibrium, so I'll get my equations of motion by minimizing the radian, which is the dissipation functional actually, and the change in the free energy. So this is what I have to write, and then I extremize with respect to velocity of biomass and velocity of water. Okay, these are my two variables. These are fields. They depend on space and time. And I'll get my equations of motion. Okay, this is standard stuff that a lot of people in polymer physics, phase separation stuff have done. So I think it might be useful to do it once, because it's pretty general, and the moment you want to add stuff, you can always come back to here and add it. So I was going to do it in some detail, if that's fine. Okay. Okay, so dissipation first. So why does the system dissipate energy? On the one hand, you have that if the biomass is sliding with respect to the water, you'll have dissipation there. And we'll assume that there is this coefficient that tells me how much dissipation is caused by the relative motion between the water and the biomass. Okay, this is a pretty general way. We can have microscopic estimates of what this zeta should be, and we'll talk about this. Then there is what is there? Well, the biomass will, there are stresses caused by the biomass itself, and if the biomass is moving, these are the forces that the biomass is exerting on itself, and this is the dissipation then. Okay, so sigma is the stress tensor of the biomass. In order to make progress, we'll have to assume that the biomass is something, and we'll assume it's a viscous fluid, very viscous, okay, with a viscosity much larger than the viscosity of water. Then there is the same term for water. Turns out this is typically very small, but same thing, okay, water stresses and velocity of the water. And then I have a Lagrange multiplier to enforce incompressibility, but we'll have to discuss about this because it's not obvious that the biomass or the water will satisfy this equation. So we're going to have to discuss what this V is. I'll do it in a second. Okay? And then what I want to model really is the fact that there is a change in the free energy due to mixing, right? This is what the physics behind this, the intuition that we are just trying to implement that comes from your colleague is there are polymers, and gradients in these polymers will create differences in the osmotic pressure, essentially, in the chemical potential of water. So water will go one way or another because there are gradients in its chemical potential. And the way you do this is you assume that there is a free energy, okay, that depends on phi. How much does that change? Well, if that depends on phi, I'll have to do the partial derivative with respect to phi, and then I'll have to multiply by the derivative of phi. Okay, and so we'll have to discuss about this too. Okay. From here, you could add a lot of stuff. Pretty much anything that's been proposed. You can add surface tension, you can add wetting, you can add everything that you think might be relevant. Okay, so continuity for biomass and water, and what is it, this velocity? Okay, so by the way, this Lagrange multiplier enforces incompressibility of this velocity. Okay. Okay, so okay, continuity. Lisa's talk was perfect for this. Okay. So what I'm doing is here is just for a second, and to make sure this is clear that these are two different phis and two different velocities, I've added B and W for biomass and water. Okay, we'll move back to this in the next step. Okay, this is the continuity equation where I'm adding a source term for the biomass, because the biomass is converting water and nutrients in biomass, right? Bacteria are doing this. This is an effective description, right? You are supposed to, just one second, you're supposed to write an equation for the bacteria and an equation for the polymers. So, and here I'm putting everything together. The bacteria are producing biomass and the polymers are not producing biomass. Okay, so I should make a distinction, but as long as the polymers are a small fraction of the volume taken by the biomass, that's fine. Yes?
So the term which you say which V are you?
Yes. Next step. Just give me 1 second. Yes.
What's G here?
G is the growth rate. Okay, it's the source of biomass. Okay. Okay, great. So now we add this two, and we have that dt of phi biomass plus phi water plus divergence of phi biomass v biomass plus phi water v water equal G minus G equals 0. And phi b plus phi w is 1. So this goes to 0. That says that this velocity, for this velocity, it is actually true. So V is the volume averaged velocity of biomass and water. Okay, in each volume, you look at how much biomass there is and how much water there is, and then you make the average weighted on the volume fractions. Okay, this is what V is here. Okay? Yes?
Like conservation of momentum, since we don't have external forces. So this is the center of mass somehow.
So we do have, so we have growth, okay? So this causes changes in chemical potential, and this causes the thing to move. So there are forces that are exerted on the system. They're not caused, they're caused by a force and a force induced by this term that we haven't explicited yet. It will come up in the next, by making the derivatives, it will become clear. So in the system, what drives the system is biomass growth. This modifies the free energy, and this causes forces, osmotic forces. Okay, so it's like a gradient in pressure.
Okay, but if you consider the whole system like
Of course, this is a closed system, so if you sum everything, then yes.
This is actually what this is actually that this weighted sum of the velocity fields are not are incompressible, because I'm like you said that in the ball there's like a lot of space for the for between the bacteria, so there's room for compression,
Yep.
which means that presumably I should be able to compress.
Yes, you can compress both of them separately, but not the average. We just derived it. This is not an assumption, right? I just said, I sum these two, and I'm not imposing that the divergence of VB or the divergence of V water is 0. What's 0 is the divergence of this volume average. And it comes out. It's not an assumption. You just sum these two and you get it.
Like what I'm saying, implicitly, water is not compressible on its
No.
own, right?
No.
But the fluid is compressible, like the biomass is compressible.
Yes, potentially yes.
Like how
Doesn't really matter. I mean, look at, you sum these two, you get it, and that's fine. You don't have to make assumptions about how things go. In fact, you might be right that in the end you don't even have to derive it, that it comes out from first principles, but just right now I don't think it matters. But we can talk about it.
In fact,
Yes.
Phi is not the density of water, but it's a fraction of water. So you can compress it. Adding
You can change the fractions. You cannot compress the... So the relative volume fractions will vary. So even if water is incompressible in itself, it doesn't translate directly in divergence of VW equals 0 because the phase can change. So you can compress it in the sense of there can be transfer between the two phases. Yes?
I think I missed this on the left side. What is the W? Or no, the top of it.
Dissipation. Okay. So now we are ready, and we'll see where forces come from directly from making the derivatives. Okay, so that actually, let me write it in a way that will make it easier to do it. Then we have this. Actually, this is all the same. Sorry. And then we have divergence of V, which let's write it down explicitly, it's a divergence of V biomass phi. Let me get back to the original notation. Okay, where do I write it? Here. Phi B is equal to phi, and phi water is 1 minus phi. Okay. And then we have that term. And let's write down what's the derivative of phi. We have it here. It's G minus the divergence of phi VB. Okay? And now we are ready. So we'll do first the derivative with respect to VW. And what we get is yes. Sorry, there is a square, and so this goes away. Okay, first term. This does not depend on the VW. Here, it's just the divergence of sigma W. Here there is VW, so this is minus P divergence of this guy. So you'll have to do one integration by part. You get a plus sign, gradient of pi times 1 minus phi. Is the sign right? This is minus 1 integration by part, gradient of p, yeah, should be right. Okay, and then there's no VW here. So this is equal to 0. Okay. This goes the same for the biomass. Okay. VB is here. Again, same trick. One integration by part, the P gets the gradient, and then we have phi. So this is plus phi gradient of P. I hope that the signs are right. They look right for the moment. Okay. And then what do we have? We have this guy. There's VB here, so I'll do the derivative. And what do I get? Again, integration by part. I'll get a gradient here. So there is a minus because of the integration by part, but here there is another minus. So this should be a plus gradient of df over d phi times phi. Okay? Makes sense? Okay, now you have to remember the definition of osmotic pressure. Actually, if you remember this definition, then you realize that this is just the gradient of pi. Because if you do the gradient of pi, you'll get the gradient here times phi plus df over... let's make it. Then there is plus df over the phi gradient of phi. And then there is minus gradient of f, but f is a function of phi, so I can write this down as df over d phi gradient of phi. So this goes away, and this is exactly the term that we have here, so this is the gradient in osmotic pressure. We are almost there. Now we can understand the equations in a second. Now, as I said, the minimal model that one can think about for this guys is a two-fluid model where the water is water, so it is a Newtonian fluid, and we'll assume that the biomass is also Newtonian fluid. You can make more complicated models and things will look different.
You should remind people what the Newtonian fluid.
It's a fluid where you have viscous stresses and you don't have elasticity, as opposed to non-Newtonian fluids where things might become different because you respond differently to a stress. A fluid responds to a stress by flowing. A solid responds to a stress by deforming. It doesn't flow. There are materials that are either fluid at all scales, space and time scales, materials that are solid because they always respond in this way to stresses, and then materials that are in between, that for example will respond in one way at small time scales that might respond as solids, but then if you wait long enough you see that they flow. And these are non-Newtonian fluids. Okay, so when I say a Newtonian fluid, it's just to remark that there is no such memory effect taken into account. There is no viscoelasticity. Viscosity is one number. For these non-Newtonian fluids, viscosity might depend on the frequency, how you exert forces onto your system, and it might change. It does in general change. Okay, so for this, in these cases, these terms are simply written as the viscosity. Here will be the viscosity of water, okay, times the Laplacian of the velocity. And this, since this is also a Newtonian fluid with a different viscosity, I will write it like this. So this completes the model. I don't have any other arbitrary choices to make, and I can see what this gives me. Okay, and I might challenge the model and change it, but this is enough to at least see what this gives me.
So what is phi?
Osmotic pressure. Okay, I would like to leave that there. So maybe I can write here. Okay, so now we can look at this, and if you sum these two, there is a phi gradient of p, and this is 1 minus phi gradient of p. So if I sum these two equations, I get a gradient of p here. Okay, this goes away. Okay, and this I have because the viscosity of the biomass is much larger than the viscosity of water, and the velocities are the same order because they are going the same way, I typically can neglect this. Okay, and this remains. Okay, so if I sum the two equations, I'll write it down here. Sum 1 and 2, let's label them so that becomes more clear. Okay. So the first term goes away. The water stress, I'll get rid of it. I get mu b Laplacian of VB. Then I sum those two. I get the gradient of P. And then I have plus the gradient of osmotic pressure. Okay? I hope the signs are right. And they're not, because there's a minus. Okay. Let me write it like this. This is wet. Okay. Somebody recognizes this equation? Yes, it is. It's the Stokes equation. So that's great. This is a simple equation. So the biomass is moving. Remember, it's a slight modification because there is pi. So as I said, G, the growth rate, the biomass growth is modifying phi, which is modifying pi through some kind of constitutive law that I haven't explicited yet, okay? So pi I will have gradients in osmotic pressure caused by biomass growth, and this puts the biomass into motion. Okay, this makes it move. Okay, what about water? So this term, we'll get rid of it, and I remain with another pretty simple equation. Equal VB, so this is just equation 1, I'm just rewriting it. I get a minus, which I'm not sure is right. So this is the sum of 1 and 2, and this is just 1. Yes, it's right. Okay, somebody recognizes this equation? Yes, that's the second one. You said Stokes, right? Good job. Okay, the equation of Darcy is an equation that tells you how fluid flow occurs when you have a porous medium. Okay, so this equation tells us that if the relative motion between the water and the biomass, it comes from gradients in pressure. Okay, and this is also a very well-known equation. So we are happy because we understand what's going on. And now to make this, like to massage this into a simpler form, because remember, the question that we started with was, does the biofilm swell or spread? Okay, and everybody thought it was spreading, and then I was surprised, and then we didn't know what the forces were, but now we sort of had ideas, so we built a model. Now we have the equations, and we can just put them in a computer, or we can do something that people in fluid mechanics often do, which is try and find a small parameter and expand in that small parameter. And here it's pretty obvious because the biofilm is much larger than it is thick. Okay, so the radius of the biofilm is much larger than its height, and so you can make a thin film model. So you say h over r is much less than 1, and then you expand. Okay, this, I don't think I can do this for you because it takes too long. Essentially, so the crucial observations is that, so you can read this in any fluid mechanics book. They're called Lubrication Models, Fin Models, and they are broadly applied, so you'll find any sort of version of it. The only thing that you have to pay attention here into making your asymptotic arguments is that there is growth. So normally in a thin film model, you just assume that because the biofilm, the film is large and it's thin, then the velocity in this direction is much larger than in the vertical direction. Just because if you have that the divergence of V is equal 0, and you write it as dxu plus dyv, if u is what u divided by r, and this term you estimate it as v divided by h, because r is much larger than h, u must be much larger than v. Okay, and this is the key for typical fluid thin film models. But we cannot do this because we have growth. Okay, so in our case, these two velocities will turn out to be same order of magnitude for the argument. Okay, to get the thin film model. This is the one major difference, and then there are some subtleties about boundary conditions that I won't discuss. Okay, so now there is a big black box. Which is the thin film model. Okay, and you'll have to believe me that you end up with an equation for H. Okay, well, I'll discuss everything. Let me write it down. Okay. Okay. So the way you get this is by integrating your velocity in the z direction. Okay, so we are here, we have a velocity, and you just make mass conservation but integrate it in z. Okay, because you integrate between 0 and h, you get an equation for h. Okay, not gonna be able to give you more intuition, I think.
What's HR?
HR is, okay, so let's talk about this more. So h of RT, do you read if I write here? Is it too low? H of RT is the shape of the biofilm, assuming cylindrical symmetry. Okay, so we'll assume that it depends on the distance from the center, which is R. R is distance from center. Okay, and on time.
So the subscript is a derivative?
Subscript is a derivative. Should I write it? HR equal dH over dr. Makes sense? Do you understand the notation? Yeah, sorry, here I don't know why I always write it this way. It's a mixture of notations, but I don't know why. Is this confusing? Should I write the... Okay, I'll assume this is not confusing.
Because then there's another derivative of the whole parenthesis.
Yeah.
So
This
why
is
don't
the-
you just write, delta?
Should I write it? Yeah.
You
Okay.
don't have to erase this.
Better? Okay. So this equation, so I'll give you an intuition for what this equation does. And then we'll solve it, because I think it's instructive to see it once. It's a self-similar solution. There's a couple of tricks, so I think it could be useful. And if you're bored halfway, you tell me that that's useless. Oh, okay. Do I have 15 minutes?
Yeah, you have 15 minutes.
Okay, I was very slow. Okay, so maybe I'll skip that actually, and I'll just give you the intuition, and then I'll show you some results. I don't know, what do you want to do? Or I'll keep going in the next lecture.
I think it's instructive to see the solution.
Okay, so let's see the solution, and then...
Unless everybody knows what it is and has seen it and has seen the trick.
Okay. Well, there is one, oh yeah, and I'm not going to be offended if you leave. So first the intuition and then the calculation. And then if we're not done, we'll finish next time. I won't rush it. Okay. Intuition. Let's take this away. What does this equation tell us? Take this term away.
That's easy.
Exponential growth.
Great. Does that spread? No. So if this is small, then there's no spreading. Agreed? Okay. Now, even if this is small, do you think it will eventually kick in? Somebody.
Yes.
Why? Okay. Exponential growth. H is growing. It's growing exponentially. It's very fast. What does this K multiply? H cube. And then there is a derivative. So all things being equal, this will eventually become larger than this or equal to this. Okay? So this is the intuition. K turns out to be a very small number, but it doesn't matter because if you wait long enough, the biofilm will be thick enough that it will expand. And this gives in the intuition that we had at the beginning. We need gradients. And these gradients develop when H at the edge is much smaller than H in the bulk. Okay, so I need H to be large enough so that there are horizontal gradients. Yes?
But this equation is also saying that, okay, so you initially grow exponentially with rate g, right? And then eventually, so h becomes sufficiently large that h cubed times the derivative of h becomes of the order of h. So then you saturate in the growth.
The H cube times H must be order 1 over K, much larger than H.
That term becomes of the same order.
This term
size
becomes,
of H,
yeah.
And so then you saturate.
So then we are not saturating because G, we're going to take it constant. But what this says is that these terms kick in. Okay? And this term, what this is it's a flux. It's a derivative in R. So this is a flux. You can think about it as really as a fluid that's going downhill. Okay, this is the flux term of that fluid that's going, of that layer that's going downhill. Okay, yes? Why? This is the black box. So it always comes in H to a large power in thin film models. I don't know how to give you an intuition. This is really the black box. It required a lot of time to do this properly. You have to solve these equations. You solve them explicitly, okay, under assumptions. And then you have to check that those assumptions are self-consistent. So you make an assumption, you get something, and you verify that at least your solution doesn't violate that assumption. So that's self-consistency. It's not a direct proof, but it almost always works. So then you couple it with a numerical simulation and you're good. So it's really a deep process, but I cannot give you an intuition for why
You
it
can get it
could.
from dimensional analysis. I guess then you can fudge K, whatever.
K it's just the parameters. So
Then you need it to be cubed in order to have the dimensions. Once you put in the derivatives, you need to have something that balances the derivatives to give you H.
But you could have had an R squared.
there is R though.
Yeah, that's true.
Yeah, because there is a lot of stuff in here. It's not like I'm sure I could come up with something, but yeah, I'll think about it. Okay, so let's start the self-similar solution of this equation, which is, by the way, it's just a nonlinear diffusion equation, right? You put this on this side, and if you define D as K R over R H cubed, this is a nonlinear diffusion equation, right? Okay, let's see if there is another one here. No. Here. Okay. Okay, now let me write it down here. Okay, the first part is eliminating this, so that's very simple. Okay, so if we write it down with H, And now I have to put the right number of exponentials. I have 1 here, and 4 here. So 3 remain. Good? Okay. Now I want to eliminate this guy, and this will be done implicitly. So remember, R is R of t, and it's the radius of the biofilm. Maybe I didn't say this explicitly. It's this guy. R of, oh yeah, I wrote it there. Okay? And I want to eliminate it for a moment. Okay, so I'm going to say that H tau, I'll normalize time implicitly. I'll say that it is like the derivative in the original time variable times R A e to the 3gt times k. This is implicit, of course, because I don't know what R is. So I don't know what tau is, but we'll get an equation for R. So we'll solve for it.
I'm a bit confused.
Yes.
I thought that the radius of the function was given by the shape of h, of the function h,
Yes.
of r.
Yes.
So how could it be possible that?
That we can solve for everything. Yes. There is no equation for R, but so this in fact is like an integral differential equation, right?
Okay.
Because R depends on H.
Okay.
But we're going to make an argument that gets us out of that.
Okay, so r.
So
is
that's
the
really
h.
great. Yes.
Okay.
So given H, you have R, and now the trick will be try and decouple the time and space dependencies so that we'll get a solution for both R and H. Good. So now with this new variable, I can write this down like this. And I'm missing one R here. Okay? Zack. Good? This was a trick, actually.
No shit.
It took us time. Okay, good. Not. Okay. Now, next step is self-similarity. Okay, this is something you do all the time. And it's really powerful, so I think seeing it once might be useful. So I'll do it for you. Okay, let me write time explicitly here. So this is crystal clear what this is. Okay, this is called self-similarity. Okay, so you're assuming that your H does not depend on time. Sorry, this is tau now. Huh? You're assuming that your H does not depend on R and X and tau separately, but in this combined way. Okay? And let's see if we can solve it. And if we can, then let's see if it's reasonable. Okay? By the way, you have to assume that this is R squared just by mass conservation. Right? We are in cylindrical coordinates. So if you do the integral of H times 2 pi R in the R between 0 and infinity, you want this to be a constant, because now we have taken away all of the possible contributions that would make this equation, this solution change volume, right? We are trying to solve now this equation, and this equation conserves volume. Okay? So because this equation conserves volumes, you want H to always have the same volume. So you can calculate it, And this is why you need r squared here. Let's see if it works. It should. So it's f divided r squared times 2 pi r dr. Okay? And f is a function of x, sorry, r. You're now wondering what's x, right? Is everybody wondering what's x? Yes, it was r. Sorry. Okay, and now the trick is I rewrite this in the self-similar variable, which is r over r, small r divided by big R. This is psi. And so this is f of psi times r divided by r is psi. Okay, 2 pi remains. And then dr divided r, big R, is d psi. Okay, so this works. That's why you need r squared, because this now does not depend on time anymore. Okay, you decide on your, you find your shape for f, and the volume of your solution will remain constant. Okay, and now we're almost done. I think we might get through it. Okay, so now we are ready to write down this equation for f and for r. Okay, we've separated the space dependence and the time dependence. Okay, so h tau will be the derivative with respect to tau goes here and here. So I have two terms. One is minus 2 1 over r cubed times r dot times f. Okay, I've done the derivative with respect to this term. Now I have the other one. Plus 1 over r squared times the derivative of f with respect to its variable. So we'll call it f prime times derivative with respect to time of psi. It's r divided r squared with a minus times r dot. Just a second. So there is a minus r squared, r dot. Okay, now I'm calling, just to be clear, f prime is df over d psi. Psi is r over big R. And r dot is dr over d tau. We're not done yet. This is just h tau. This is just this part. There was a question. Can I finish this and then we got the question? Then there is minus 1 over r. I have r here. And then I have h cubed, which is, where is it? Here. F cubed divided r to the 6th power. Cool? Okay. hr is what? 1 over r squared f prime, except that now f prime is the derivative of f with respect to psi. So I get 1 over r, right? df over d psi equal 1 over r, sorry, the opposite. Right? Okay. So I get 1 over r from here. And now I have another derivative with respect to r here. So this will be another prime, but I need to put another big R here. Okay? Good. Okay, so now I'll write here so we can keep both. Is this good? I think it's good. Okay, so now we're almost done. Let's write this. My goal for the next step is to eliminate R. I only need Xi. I want Xi. Okay, can I do it? Well, from here, so let's take R cube out. Let's take R to the 4th power out. There's a minus. Minus F prime R4, which I put there, and R. Now one of these actually okay, this works. Let's see if this works. R over R, so I eat one R from here and I write it as Xi. There is F prime, okay, and then I have R cubed at the denominator, okay, and that goes there. There is a 2 here. Okay, what else? Another minus. Let's see if it works. Minus 2 R dot F R cubed. Okay, this should be right. So can I take R dot outside without you killing me? Let's do like this. Okay. And then this, we'll put it on the other side, okay, just because. And we have 10 R's at the denominator, and we can write 1 over Xi and Xi, okay, instead of 1 over R and R, okay. So 1 over Xi, Xi, F cubed, F prime, prime, and then I have 1 over R to the power 10. Yes. Okay. Now the trick is this worked. So once you get here, it means it worked. Why?
You have a linear term on the left.
It's not, I mean, the question is not whether this has a solution, whether it's nice, but it worked in the sense that I made this trick. I assumed that my function would only depend through this combination of stuff, and now I don't have R anymore. I only have Xi, a small r. I only have Xi and big R, and I can separate that equation. So it worked. Even if I need a computer now to solve it, and because it's too complicated, it worked. It turns out I don't need it because this can be solved explicitly, but it worked. Okay? So first, the equation for R, which is, now remember, this is a derivative with respect to tau. So dr over d tau equal 1 over r to the power 7. And we'll go back to see what tau was. Remember, we rescaled it implicitly in this way. Okay, so we can go back now to the original time variable. Okay. Sorry, 7. this can be solved. Solved. This is kind of magic. I mean, I'm trying to joke about it to point you to this magic that occurs when this works. And this tells us a very interesting thing, even at first sight, which is R, through a complicated dependence, but it doesn't matter, will start constant, and then eventually, when this stuff becomes large enough, it will start to grow. Okay? So there is a memory, there is some time that you need to develop in order for your gradients to be large enough to expand. Okay, so this tells us the answer to the question I posed initially. Does this swell vertically, or horizontally? And the answer is first, it goes up. First it goes up, and then it spreads.
So we're out of time. I
Yes.
suspect you want to do the other equation too?
Yes.
Do you want to do it
Tomorrow, right?
Okay.
So we'll finish tomorrow, but at least this is a nice place to stop because we solved it, we have the answer, and we are happy. We can go to eat.